Okay, everyone. So today we will continue on the lecture for MOSFET fundamental. Okay, MOSFET fundamental. From the name itself, I think you have familiar with it because you have done the what we call it, the lab, microelectronic lab. Okay, so that one you have done on the simulation for MOSFET. Okay, if you still remember, where you simulate the MOSFET device structure and then you analyze the characteristic. Okay, you analyze the characteristic by extracting all the electrical parameter from the IV characteristic. Okay, so for the first part here, more on the fundamentals. Okay, what is MOSFET? So MOSFET is the metal oxide semiconductor field effect transistor. Okay, so here is the outline for the lecture, which will cover on the two-terminal MOS structure, okay, energy band diagram. Of course, when you take this course, you cannot run from the energy band diagram, okay, from Schottky barrier diode to the PN junction, and now you have MOS structure, okay. And the depletion layer thickness, of course, the same thing. Work function difference, flat band voltage, and threshold voltage. Okay. Other than IV characteristic, in this course or in this topic, you will see the capacitor voltage characteristic. Okay. Right. So what is MOSFET? Okay. So it is a metal oxide semiconductor. So you can imagine that it is the combination of so this is your gate, okay, gate structure, and then you have the oxide, okay, so this is your gate terminal. This is the oxide layer, okay, and this is the substrate, okay. So more on the structure for MOS is like this lah. So this is the source and this is the drain. Okay, MOS structure is one of the famous way to build a transistor other than BJT. And then why transistor? Okay, because it is used in almost every electronic devices. Okay, and it has been used the application for switches, for in analog circuits, which has been used in CPUs, memory, and also in LED and displays. Okay. Other than that, MOSFET has the advantage where it has a smaller size. It uses low power because it has a low threshold voltage. Okay, compared to the other transistor, it can make circuit using a MOSFET with less number of resistors. Okay, and then it manufactured by the CMOS technology process. Okay, first of all, before we look into the MOSFET, okay, so it is actually comes from the MOS capacitor. Okay, MOS is the short form is MOSCAP. All right. So MOSCAP is like I said, it is the combination of between metal. So this is the metal oxide and semiconductor. All right. Usually metal is made of the polysilicon gate. Okay, but in your simulation in the lab last time you did on the metal gate. Okay, so but in this syllabus it will be focused on the N plus polysilicon gate. The insulator layer usually in terms of silicon dioxide. Okay, so that will be the insulator layer. All right, so speaking about the from the name itself, so you know that the capacitor is a two plate combined together, and there is a capacitive, okay, in between the two plate. Okay, that's why the name from the name itself, it is a MOS capacitor. So it is actually between plates. So in between two plate, between metal and semiconductor, there is a capacitive. Okay, so in the end of the day, we will look on the capacitance voltage characteristic, which is the trend or the character. Other than the IV characteristic, we will look into the capacitance voltage characteristic. Okay, so from the perspective of two-terminal MOS capacitor, all right, so it has by considering a p-type silicon, so this is a p-type silicon, all of these are p-type silicon. Oh, sorry. Okay, so this is p-type. Okay, so there are several connection that you can apply for your MOSFET. Okay, first is by applying negative gate voltage. For example, this one when VG less than the 0 volt. Okay, so we know that at this metal plate all are negative. Okay, negatively voltage at this metal plate. So what happened here, which is in between oxide and p-type substrate. So all we know that the p-type majority carriers are holes, so holes will be attracted towards this negative. So we know that holes, okay, from this p-type semiconductor, the majority carriers are holes, so holes will be attracted toward the negative, okay, towards the negative gate terminal. Okay, so in this case, we expected that for the first voltage application, so accumulation of hole at the semiconductor oxide interface. So semiconductor oxide interface means, so this is the semiconductor, so this is the oxide. In between oxide and semiconductor, there will be holes accumulated at this interface, okay, due to the attraction of negative metal gate. Okay, other than that, we can also apply moderate positive voltage, okay, VG greater than 0. So what will going to happen here? So there will be a large positive voltage at this metal plate. So again, this is a p-type semiconductor. So what will happen here? Okay, since the p-type, the majority carriers are holes, so holes will be repelled away from this positive voltage. Okay, so there will be a region where holes will be repelling away from this positive metal plate. Okay, what will happen here? It will create a space charge region, or that you have learned so far it is depletion region. So there will be a space charge region over here. So there is a new terms for MOS capacitor. So this is a space charge region when you apply positive voltage, okay, to the p-type MOSFET. Okay, other than that, what happened when you apply a very large positive voltage? Okay, there will be a larger positive voltage over here. Okay, of course, we will expect that there will be a depletion region over here, or the space charge region will be much larger due to the larger positive voltage. Okay, we expect that this is less positive voltage, okay, and this is larger positive voltage, and this space charge region is actually increasing. Okay, due to this, due to the very high electric field of positive voltage, okay, we know that from p type, okay, there will be the majority carriers are holes. Okay, however, in p type also it has minority carriers of electrons. Okay, due to the high electric field here, it will be able to attract some of the minority carrier of electrons from the p type. Okay, due to this, for this case, okay, where VG is much greater than 0 volt, there will be accumulation of minority carrier of electron at the semiconductor to oxide interface. Okay, from this explanation, we know that they have three types of terminal which apply, okay, to the MOSFET. Okay, first thing is when you apply a negative voltage. Second thing is when you apply positive voltage. And the third thing is when you apply larger positive voltage. Okay. All right. From here, um, uh, the MOS capacitor and the principle of operation. Okay, this is basically the same thing what I have explained in the previous slide. Okay, there is another parameter in MOSFET, which is the flat band voltage. Okay, so this flat band voltage is an important term to the MOS capacitor, where it defines the voltage at which there is no charge on the capacitor plates, and hence there is no static electric field across the oxide. Okay, meaning that from the name itself, flat band voltage means the energy band diagram is still flat. Okay, now we imagine that there is no voltage applied yet. Okay, so what will happen to the MOSFET? Okay, since no voltage applied yet, there will be no charge across the capacitor. Okay, because we're not giving any voltage and there is no electric field between the plates. Okay, therefore no charge across the plates. Okay, so these three combination that I have explained the same thing like before. So the first thing is when you apply VG less than 0. So this principle of operation, we call it as an accumulation region. So the second one is when you apply VG greater than 0. So this one, you will be able to get the space charge region, or space charge region, in other words, that you have familiar with before, is the depletion region. So it is the same. So number 2 is depletion region. So number 3, when you apply a very large positive voltage, okay, it is the same like as the second one. Okay, however, in this case, a very large positive voltage, and this one, the space charge region will become much greater, and this one we call it as the inversion region. Okay, so these are the three mode of operation that you're going to look for these topics. Okay, so what happened kept in the equilibrium? Okay, so in equilibrium means there is no voltage applied, so we expect that okay, a very what we call it, okay, the energy band diagram is flat. Okay, no bending, right? So this is actually, when if I go back, okay, so this is if I draw in upside down the structure. So this is the metal gate, so this is the oxide, and this is the substrate. So there will be a capacitive, okay, in between the plate. Okay, so the first plate is the metal, second plate is the substrate. Okay, so the capacitive between these two, since there is an electric field, okay, in between them. Okay, however, without applying any voltage, there will be no charge between the plates. Okay, so other than that, flat band voltage, also known as the VFB. All right, for this case, in equilibrium, okay, again, same metal oxide to semiconductor structure, and we expect that there will be no bending, okay, no bending, okay. Charge only exists at the surface of metal. Okay, we know that in metal, okay, metal, it can conduct current. There will be a lot of free electrons in the metal. Okay, so this is the metal plate. All right, so we assume there is no charges because no voltage supply and no dopant located at the oxide. Okay, at this we can't achieve thermal equilibrium through the oxide layer. As we can see, all the energy band diagram in the straight line, no bending. Okay, so this one is for the case of p-type. Okay, because the Fermi level is near to the valence band, and this is the energy band diagram for MOSFET for p-type. Okay, so you have still the same conduction band, valence band, and the Fermi level. Okay, of course, it is connected to the oxide, and this is the metal. Okay, when there is a voltage application, okay, we expect there will be a bending. It's whether upward or downward, depends on what voltage we apply to the MOSFET. All right. Okay, in this lecture, it will be divided into two. Okay, will be covered for both p-type and n-type in all region of operation. Okay, the first one, accumulation, depletion, and inversion. So we will look into all of these parameter and also what happened to the energy band diagram. All right. Okay, let's take a look on the first one. Okay, for the P type. Okay, for example, this one. So you have for P type, of course, you need to know voltage that are going to apply to the P type. Okay, so for in accumulation, okay, in accumulation from the name itself, you can imagine that there will be a carrier that accumulated at the semiconductor to oxide surface. So what type of carrier here that you need to know? Okay, so for the MOSFET P type, okay, the voltage that we apply is negative voltage, as you can see here. So negative gate voltage will be applied to the metal. Okay. Okay, we know that for the P type, okay, the majority carriers holes. Okay, therefore holes will be attracted towards this interface. Okay, so this is the metal. Okay, so holes now will be attracted to this metal to semiconductor surface. Okay, so in here, due to this, okay, by applying negative voltage, okay, it will create negative charges on the metal, okay, and these negative charges will attract holes from the P type, okay, and holes will be accumulated at this region, okay. Due to this, actually the electron energies are raised and matter relative to the semiconductor, okay. So more holes, if we increase more voltage, there will be more holes accumulates at the surface. Okay. Due to the accumulation, okay, at this surface, okay, at the semiconductor. So this is the semiconductor. So in the energy band diagram, so we expect that there will be holes accumulated at this semiconductor. Okay. Therefore, the banding for the MOSFET in accumulation will be upwards like this. Okay, and as well as the Fermi level also, okay, will be nearby to the valence band, and the energy band diagram for conduction band and the valence band will be moving upward, okay, due to the accumulation of holes at the semiconductor. Right. So first thing you need to know for the MOSFET, okay, since it has two type for the P type and N type, okay, how you want to make this MOSFET P type in accumulation. So that will be the question. So you need to know the most important thing is the voltage application. Okay, in order to make the MOS capacitor for the P type in accumulation region, you need to apply negative gate voltage. Okay, you need to apply negative gate voltage because you want to attract all the holes accumulate at the semiconductor to metal surface. All right, the second one, if we look at the N type, for the N type, okay, so of course, my lecture, I design it to be like first P type and then N type, P type, N type, so that you can see the difference between the operation of P type and N type. Of course, for the N type, it is vice versa from the P type. Okay, for P type, you apply negative gate voltage. For the N type, of course, it is vice versa. You will apply positive gate voltage. So this is the positive gate voltage. Why you apply positive gate voltage over here? You know that the N type, the majority carriers are electrons. Okay. Okay. However, for the P type, the majority carriers here are holes. So holes will be attracted to the negative, and this one electron will be attracted to this region. Okay, due to the positive voltage at the metal. Okay, when electrons attracted over here. Okay, so this electron is actually at the semiconductor for the conduction band. So this electron, the accumulation of this electron inside. So this is the positive gate voltage. Okay, so inside the energy band diagram. Okay, so the accumulation of electrons is at the conduction band. okay, at the conduction band energy. Due to this, the energy band diagram will move downward. Okay, so the energy band diagram will move downward. All right, like this. Okay, so we expect that, of course, in both. Okay, the both will be bending. Okay, but the bending is depends on the type of carrier accumulated at the surface. So which surface I mean is, so this is the metal and this is the oxide. Okay, and this is your semiconductor. Okay, so the surface is at the oxide to semiconductor. Okay, so this accumulation is between oxide and semiconductor, and this is your semiconductor, right? So up to here, you need to know how to make a MOSFET in accumulation. Of course, the voltage application is positive gate voltage. Okay, why? Because it will be able to attract the majority carrier of electron from the N type, okay, to the oxide to semiconductor interface. And the energy band diagram, it will be moving downward because all the electrons, okay, from the majority carrier electron N type will be moving accumulated over here, and the energy band diagram will move downward. All right, so next one is like I said, first is accumulation. Okay, second one is when you apply opposite voltage. Okay, there will be from the name itself, depletion. So you expect there will be a depleted area. So depleted area, where? Depleted area underneath the oxide. Okay, so let's take a look over here. In this case, right. Oh, sorry. All right. So in this case, you have in accumulation, you apply negative gate voltage, but in depletion, you apply vice versa voltage, which is the positive voltage over here. So this is positive V gate. Okay. So this positive voltage, you know that this P type, okay, the majority carriers are holes. Okay, therefore holes will be repelling away from this positive. Okay, from this positive, so there will be holes repelling away, and it will create a space charge region or a depletion region. So this is in other word, okay, it could be the depletion region. Okay, or in other word, the name is also space charge region. Okay. All right, so it could be depletion region or space charge region. Okay. However, because some of the minority of electron also will be able to be attracted. Okay, if this Vg is increased, so this one happen in the inversion. Okay, let's take a look over here. When Vg is positive, okay, there will be holes repelling away, and it will create a space charge region. In this case, there will be a slightly bending over here, okay, at the holes over here. However, this bending is a very small bending, okay, a very small bending, and it will create a induced space charge region. So this one, it could be the notation is XD. Okay, some book use W and some book use XD. So this XD is represent as a induced space charge region. Okay, why there is a bending over here? Because this voltage also able to attract the minority carrier of electrons. Okay, so minority carrier of electron will be attracted across this region. Okay, and this one, so this minority carrier of electron is actually over here. Okay, and then there will be a small bending bend down. Okay, due to the electrons accumulate minority carrier of electron accumulated at the this interface, right? So it's however, this is for p-type depletion. All right. So what happened for the n-type depletion? So of course, it is vice versa to what you see in the accumulation. Okay. So in accumulation, you for the n-type, you apply positive voltage. For depletion, you apply negative voltage. So this will be a negative voltage over here. Okay. So negative again here. Okay, negative voltage. Again, you know that from here, the majority carrier of electron will be repelling away. So because of the negative voltage, so due to this repelling away, so it will create induced space charge region or depletion region. Okay, because of this depletion region, okay, in the energy band diagram also there will be a bending, okay, due to this. All right, so this bending is actually the holes that the minority carrier holes from the n-type that is attracted over here, and that's why it is moving upward. All right, so this is quite different, okay, from the accumulation. However, this depletion region will create a new parameter called XD. Okay, so this XD is represent as the depletion region or the induced space charge region. All right, so the final region or the final mode of operation is inversion. So it is still the same like in depletion, okay, where you apply positive gate voltage. However, now you apply a very large positive voltage. Okay, so this positive voltage is much larger. So we expect that a lot of positive voltage over here, and due to this all the electrons, okay, all the holes, okay, from the p-type over here, okay, will be repelling away and creating a larger space depletion region. Okay, due to this, okay, due to the high positive gate voltage, okay, and it able to attract the quite number of minority carrier of electron from the p-type. Okay, so this minority carrier of electron will be accumulated here. Okay, still the banding is moving downward. Okay, same like in depletion. However, now due to the a lot of minority carrier of electron accumulated at the surface. Okay, therefore the banding is moving so much downward. Okay, still it has the XD. Okay, it has the parameter for the space charge region, which is XD. Now the XD become maximum, and they name it as a XDT. Okay, so this is what happened during inversion. Okay, during inversion for p-type semiconductor. Right, so the depletion region will be extended, okay, and the new name will be XDT. All right, other than that, for the n-type, okay, n-type inversion, same goes to the n-type for depletion. Okay, the voltage application is negative, but now is much more negative. Okay, so negative gate voltage will be applied over here. Okay, but now this negative gate voltage is much larger um, in magnitude. Okay, so the electron, okay, the electron from the majority carrier of electron, okay, will be accumulated over here. Okay, will be accumulated over here, and due to this larger gate voltage, okay, there will be an electric field that able to attract the holes. Okay, so this minority carrier of holes, okay, will be accumulated here, okay, and it will create an inversion layer of holes. Okay, in this case, depletion region, okay, of at the inversion mode of operation will be increased. Okay, due to this, the bending is moving so much upward. Okay, as compared to the depletion just now. As compared to the depletion that just now, there is a bending upward. However, in the inversion, the bending is still upward, but much larger, and it will be able to create the XDT as well. Okay, XDT is the term for the induced space charge region in inversion. All right, so let's take a look. If you have uh, see the three types of mode of operation, and then how the energy band diagram moving, okay, downwards and upwards. Okay, now let's take a look on the parameter. Of course, you're gonna have the same parameter. Okay, in this case, for example, for the case of P-type semiconductor. Okay, for the P-type semiconductor, if you look at in the previous slide, okay, for the P-type semiconductor, you have in depletion, you apply voltage, positive gate voltage, okay, and then the bending is moving downward, okay, moving downward like that. All right, so in this case, there will be a parameter XD. So what is XD? It is a depletion width, or the induced space charge region. Okay, in this case, due to this bending, okay, you know that from the energy band diagram, you have work function at the from phi s for the semiconductor, and then work function phi fp for the Fermi level at p type. Okay, so this one, the potential or the phi fp is the same like you have learned in the previous lecture. So phi fp, it is the same, equal to the vt ln na over ni. So since this is for the p type, so we are using the Na, the acceptor concentration. Okay, Vt is Kt. Okay, the same thing. So pi Fp, Kt ln Na over Ni. Okay, so the Ni is depends on the type of semiconductor. If it is silicon, then you take the silicon value. So space charge width, okay, it is the same. Like you have learned in the previous lecture. Okay, you have also xn and xd, if you still remember, xn and xp, so it is the same. So the equation is 2 epsilon s phi s over e and a. All right, for the surface potential, surface potential is the difference between the Fermi level minus the Fermi level for the Fermi level at bulk minus Fermi level at the surface. Right. Other than that, so this is in depletion. Okay, in depletion. Okay. However, what happened in during inversion? Okay, this is during inversion. So you know that during inversion, you apply a very large positive voltage over here, and the space charge region now being extended to the XDT. Okay, because the depletion width increases, okay, due to the accumulation of minority carrier of electrons over there, and the XDT will be extended. Okay, what happened here? So the bending now is much larger. Okay, and it will create an XDT. So this XDT is double actually. So in this case, during inversion, it is assumed that the phi s, the surface potential, is double to the phi fp, which is equal to the threshold voltage. Okay, so this is the assumption made by the Niemann. Okay, during inversion, the surface potential is actually double the surface potential phi fp, and then it is equal to the minimal voltage to turn on your MOSFET, which is threshold voltage. Right, so the maximum space charge width also will be double. Instead of 2 epsilon s pi fp, now you have 4 epsilon s pi fp over E and A square root. Okay, all this, I think all this parameter you have familiar with, the xdt and so on. This is the same from the first topic of this lecture until today in MOSCAP. So you're going to have the same kind of parameter. Okay, the depletion width, the space charge width are all the same. Right. And second one, in the case of now we're talking about for the p type. So this is for the p type. Okay, for the p type, and this is also for the p type. Okay, what happened for the n type? Okay, for the n type, of course the banding are different. Okay, between n type and p type. Okay, for the p type in inversion. Okay, for the n type in inversion, if you look at the previous slide, so n type during inversion, you apply negative gate voltage. Okay, so when you apply negative gate voltage, the majority carrier of electron from the n type, okay, will be repelling away, and it will create a larger inversion layer. Okay, or this induced space charge width will be larger. Okay, due to this, this from the n-type semiconductor, it has minority carrier of electron holes. So this minority carrier of electron will be attracted a little bit at the surface and will be accumulated here. And that's why this bending will be much bending upward. Okay, right? Due to this, okay, same thing. Okay, for the p type, you actually find the phi fp, but for the n type, you're going to use the formula for the phi fn. Okay, instead of using na, now you have donor concentration. Okay, the same thing for the n type. Okay, it is assumed that the surface potential phi s is double to the phi fn, which is equal to the minimal voltage to turn on your MOSFET, which is the threshold voltage. And the xdt, now instead of using phi fp, you have phi fn over nd. All right. So yeah, after understanding the mode of operation, how it bend upward and downward, now you look at the example. Okay, for the example, of course, I think you already familiar with the calculation, okay, up to now, because next week you're going to have the test. Okay, so for this one, for example, given calculate the maximum space charge width. Of course, you have to know maximum space charge width is xdt. Okay, maybe in the test later also I won't be writing exactly like this xn or xp, but make sure you know. Okay, it is a space charge region. Okay, for a given doping concentration, consider silicon time equal to 300 Kelvin, dope with to Na equal to time to power of 16, and the intrinsic carrier concentration 1.5 times to power of 10, right? So in order to, this is quite straightforward. Okay, you have to find the phi fp. Okay, so this Vt is actually equal to Kt and 0.0259. All right, Na given is 10 to power of 16. Okay, and I also given. If it is not given, then you have to find at the appendix. Okay, so all the values during test later will be given in the appendix. Okay, this is in the test, it is not like straightforward like this, all the values given in the question. No, you have to find yourself in the appendix. All right, so phi fp is equal to 0.3473 volt. Okay, so xdt, maximum space charge width. Okay, just take the equation. Okay, 4 epsilon s phi fp over E and A. All right, so just plug in all the values. Okay, and then you will get the xdt equal to 0.3 times 10 to the power of minus 4. Okay, you don't have to convert to the micrometer, just take femtocentimeter. Okay, to avoid careless mistake for further calculation lah. So basically, for this example, this straightforward, just ask you to find the XDT and so on. But for the test, not this test, okay, this test not cover on the MOSCAP, no. Later you have to find further calculation lah. So better to stop until centimeter. All right. Okay. Other than that, what is surface charge density? Okay, I think this example is quite straightforward. You can do it yourself. Okay. For the surface charge density, there are other parameter. Okay, which is not really common parameter, but I just want to introduce it to you. Okay, during for the P type. Okay, during inversion. Okay. All right. So during inversion, there is a surface charge become larger. Okay, so during inversion, for the P type, okay, this region will become larger. Okay, so the space charge region is actually increasing. Okay, due to this, actually, there is a surface charge density. Okay, so this density is actually due to the trap of electron and minority carrier of electron for the case of P type. Okay, so you can find this surface charge density. Okay, so this is not really common, but this is how they find the surface charge density, which is equal to the ns equal to the ni exponent phi fp over vt time exponent different phi s. Okay, in this case, during inversion, phi s equal to the 2 phi fp. All right, so ns equal to the nst exponent blah blah blah. So what is nst? So nst is the surface charge density equal to this equation. Okay, all right, so vt over here is the vt over here is the kt. Okay, kt, not threshold voltage, not vth. So this is the kt value, which is 0.0259. All right. Okay, so this surface charge density, okay, is increases as the phi s increase. Okay, when the surface charge potential phi s over here increase, okay, this surface charge potential increase, okay, the surface charge density also increase. Okay, when there is the larger potential, it is expected that the larger surface charge density can be found in the depletion region. Okay, so it is actually proportional. So nst is proportional to the phi fp, proportional to the phi s. Okay, because phi s now is equal to the 2 phi fp. Okay, as the two surface potential increase, it is also increase, and this is quite straightforward because it is linearly increase as the surface potential increased. All right. Other than that, okay, since the combination of MOSFET is between metal and oxide and then semiconductor. So this is between two plate. Okay, so this is the metal, okay, oxide and semiconductor. Of course, between these three itself, between metal to semiconductor, metal to oxide, metal to semiconductor, there is a work function difference. Okay, there is a work function difference. Okay, so inside the metal itself, okay, inside metal itself, it has the work function for metal. Okay, however, inside the oxide also it has the oxide electron affinity, and inside the semiconductor also it has electron affinity. So all this has its own work function value. Okay, work function value. Okay, so what happened when it is bending? Okay, so for example, this is the p type. Okay, in inversion. Okay, in inversion. Okay, so the energy band diagram is actually moving downward, okay, due to the voltage application just now. And also inside the oxide, which we couldn't see, okay, there is a bend, a little bit bending, okay, due to this bending as well, okay. So this oxide also will bend downward, okay. What happened to the metal? So metal is not going to bend, okay, because there is a lot of electrons, free electrons at metal. So it is hard to predict what happened inside the metal. So usually metal will have a straight work function like this, right? So this is actually the MOS system, okay, inside the MOS. So this is what happened. So basically the bending usually referring to the at semiconductor, okay. What happened inside the oxide? It says there is a slightly bending, okay, due to the bending at semiconductor, and at the metal there will be a straight line of the metal work function phi m, okay. So this is exactly the system inside the MOS structure in equilibrium after applying contact. All right. So this is since there is a bending, and then there is the voltage related and so on. So it is quite complicated, okay, to find the metal work function. So now I introduced to you the metal to semiconductor work function, okay, from the metal itself. So this is metal. And then semiconductor, it has phi fp, okay. You know that phi fs is equal to the phi fp during inversion, okay. So if we look at the derivation over here, okay, so the VOX, so VOX over here, the voltage at oxide plus the phi s equal to the this one referring to the metal, okay. Different work function at metal and different work function at semiconductor. So it is actually the different work function at metal and semiconductor. For semiconductor, the total will be the chi plus energy gap over 2 plus 2 phi fp. Finally, after the derivation, so there will be a new parameter phi ms. Okay, phi ms is the metal is the work function from metal to semiconductor. It's equal to the phi m for metal minus the total work function at semiconductor. So this is the total. Okay, so VOX plus phi s is equal to the minus phi ms. So this is the metal to semiconductor work function. All right. So this is a new parameter in MOSFET. Okay, there will be I think you couldn't find this parameter in the previous topic. So this is a very new parameter which is work function between metal to semiconductor. All right. So you can calculate this metal to semiconductor work function if all the parameter given here, for example, the metal work function, and then you know the chi value, and then you know the energy gap. Of course, you can calculate the phi fp. Okay, if all this you know, then you can calculate phi ms using all these parameter. However, if you don't know all this value, you can find this phi ms value from the graph, okay, from the graph. All right, so this is for the case of p-type. Okay, for the case of n-type, okay, the energy band diagram is moving upward. So you're considering the same equation over here. However, now for the n-type, okay, so finally you will get the phi ms equal to the phi m. So this is referring to the metal to the work function for metal, and this is the total work function at the semiconductor. Okay, different now, you have phi fn instead of phi fp for the p-type. All right, so okay, so we have 5 minutes, right? Okay, so the polysilicon gate, okay, like I said, what you have done in the lab. Some of you might not realize that you are using the polysilicon gate. Some of you might change the polysilicon gate to the metal gate, okay, to get the desired threshold voltage needed by the by the lab sheet lah, okay. So that one, in this case, usually up to now, in Niemann, okay, they're considering the polysilicon gate, okay. So there are two type of polysilicon gate. It could be the N plus polysilicon gate, and it could be the P plus polysilicon gate, okay. So for the N plus polysilicon gate, all right, so the metal work function, okay, it is equal to this one. So chi, so this is actually referring to the metal, k phi m, minus this is for the semiconductor, okay. And finally, you will get the equation Eg over 2 plus phi fp. So this is phi ms for the N plus polysilicon gate. For the P plus polysilicon gate, okay, it is the same. Phi ms is equal to this phi chi plus Eg over 2 minus this portion for semiconductor. Okay, semiconductor, this is for metal. Okay, finally, you will get the Eg over 2E minus phi fp. Okay, so this is for the N plus polysilicon gate, phi ms, and P plus polysilicon gate for the phi ms as well, right? Okay, so work function, like I said, if all the parameter here you given, okay, for example, the metal work function, okay, like I showed you the table last time. So for aluminium, it is 4.29. It has gold 4.51 and so on. So if this value given, then you can calculate. Chi, for the silicon also, you can find the appendix if any, okay, and EG, 5N you can use. So if all this parameter given, then you can calculate manually. But if it is not given, then you can refer to this graph. So this graph is actually referring to the metal to semiconductor work function, okay, versus doping concentration. Okay, so this is doping concentration. Okay, doping concentration. So this is the phi ms. Okay, so for the metal to semiconductors, so like I said, so for the metal, it could be polysilicon, okay, and it could be for the n-type, okay, n-type MOSFET. Okay, it could also be P plus polysilicon for the metal. Okay, so this is the metal. Okay, this is for the semiconductor. This is for metal. This is for semiconductor. It could be combination between P plus poly and the P-type silicon. Okay, so as you can see, there are many lines over here. So depends on the combination of the MOS system. Okay, for example, if let's say the combination of N plus poly and N-type silicon, then the line that you can find your phi ms is this line. Okay, this line. Okay, the concentration now is depends on the question. Okay, if let's say the ND is 10 to power of 17 given, so this will be your line. Okay, for example, ND is 10 to power of 17. Okay, so therefore this will be your line, and this intersection is actually your phi ms. Okay, so this is the phi ms for this particular system, N plus poly with N-type silicon for ND times equal to 10 10 to power of 17. All right, so this work function difference is different, okay, in all combination. Okay, so if you have metal, like really metal, not polysilicon gate, between gold and N plus polysilicon, so this is the line. Okay, so we will look at the example tomorrow. Okay, in the tomorrow class. So I have to stop the lecture now. It's at 3 p.m. now. Okay, so we will look at the example tomorrow. All right, so do you have any question? Are you all still there with me?
Yes.
Hello?
Hello. Hello.
Hi.
Yeah.
Okay, any question, guys? Girls? no question. If you have no question,